Hi everyone, welcome to lecture number 11 for Physics 151. The topic for this lecture is projectile motion. This builds on the two-dimensional kinematics that we covered in lecture 10 and that are covered in the previous two sections of the textbook, 3.1 and 3.2, and it applies them to the specific case of an object in free fall that has been launched near the surface of the Earth. This is covered in 3.3 of our textbook, and toward the end of this lecture, I'll solve two of the problems for you as example problems from tutorial 11. All of the problems on online homework 11 relate to projectile motion. So we'll start this lecture with a bit of a review from lecture number 10. So much of this slide is simply a repeat from lecture 10. I want to remind you, first of all, about our vectors for instantaneous position, velocity, and acceleration. Instantaneous position vector, the vector r, just points to wherever an object is in space at any moment in time. And the velocity vector v shows the speed and direction of the object's motion at any moment in time. And I want to remind you that instantaneous velocity is always tangent to the path of the object through space. Okay, so that's a convenient thing to remember for projectiles. Okay. We're going to do something to keep our math simple. We're going to always, for all of these projectile motion problems, choose the positive x direction to be downrange and the positive y direction to be upward away from the center of the Earth or center of whatever planet we are on. So what do I mean by that? Downrange, I mean if this is a soccer ball that's been kicked or if this is a cannonball that's been fired, then choose the positive x direction to point always in the direction that the object has, in the general horizontal direction that the object has been fired or launched. The positive y direction, let's always choose that to be upward away from the center of the Earth or planet. So that way gravity will always only accelerate in the negative y direction. That will help to simplify lots of our equations, as you'll see on the next slide. Now, what's new for this slide is think back to our equations for kinematics under constant acceleration. And if you think about the one-dimensional equations, remember that equation number 1 was v is equal to v naught plus at. And equation 2 was x is equal to x naught plus v naught t plus 1/2 at squared. Okay? It turns out we can simply write those equations for vectors as well. And we replace the one-dimensional acceleration, velocity, and position with the two or three-dimensional vector. Time is just a scalar, so that's just scalar multiplication. And it turns out these equations work. So when you have constant acceleration, when our acceleration vector a is constant at all times, it never changes in direction or magnitude, then it turns out these two equations hold for vectors as well as for single individual variables. Okay. Now, this is actually a set of two or three equations. If it were three dimensions, this would be three equations. But this is actually a set, we're just going to consider the x and y direction, x and y dimensions, because we don't need the z dimension if we always make this simplifying assumption that we did up above, right, where x is downrange and the positive y direction is away from the center of the Earth. So then there's never any z motion. Okay. Then it turns out this is actually two sets of equations packed together. We can write these out, and out here, let's move on to the next slide. We can write out these equations with just the x or horizontal components, and it would look like these first two equations right here, or just the y or vertical components, and it look like those two equations right there, those first two equations. Okay, so in other words, just the x components of each of these things. The x component would be vx, is equal to v naught x plus ax times t. Now time is a scalar, so it doesn't have x or y components. It's just scalar. And if we did the same thing for the y components, it would look like that. Okay? These equations are independently true. Okay, so in other words, the x and y components don't mix. X and y components are at right angles from each other. So we can separately write a true equation for the x components and separately write a true equation for the y components. If we did the same thing for the second equation, then we would get x components and the y components for the second equation. And then the third equation is not a vector equation. The third equation is what we get when we solve for t in the first equation, plug it into the second equation, and simplify algebraically. So we've eliminated t. So remember the third equation, our equation number 3 of kinematics for constant acceleration, is just what you get when you plug equation 1 into equation 2. So it's not an independent equation. But I've included it here just because it's handy. It's often going to be handy for us to use that as well. So this is our equation 3 written for horizontal components and written for vertical components. If you were to, again, if you were to combine these first two, you'd get the third. Okay. At a glance, I'd like you to verify, right? That as you look at the horizontal and the vertical equations separately, all of the variables in each of these two blue boxes here are distinct from each other except for time. Time is the only variable that allows you to cross back and forth between these two boxes. It's shared. It's the only variable that's shared between these two boxes. Otherwise, everything else in the horizontal box is distinct and separate from everything in the vertical box. Now, what we've written here is generically true for any time you have constant acceleration for an object moving in two-dimensional space. Okay. We're going to now apply this to the specific case of free fall. So for an object in free fall near the surface of the Earth, and I want to, again, remind you that that means that there's no other forces besides the object's weight acting on the object, okay? So no air resistance or any other forces, and that the arc of the trajectory of the object keeps it near enough to the surface of the planet that the strength of the gravitational acceleration doesn't weaken, it doesn't vary, okay, over the course of the arc. So in other words, acceleration is constant. The gravitational acceleration is constant. And again, we're going to choose positive x downrange, positive y upward away from the center of the Earth. And what does that mean? Well, first of all, gravity only works in the y direction. So it always pulls an object downward, right? Law of falling bodies. Objects are pulled downward toward the center of the Earth with an constant acceleration of magnitude g. And the downward part is shown here for the negative y direction, okay? So the y component is negative, pointing downward toward the center of the Earth. And then gravity does not act tangential to the surface of the Earth. It only acts toward the center of the Earth. So the horizontal acceleration of any object due to gravity is 0. Gravity does not act in the horizontal direction, it only acts in the vertical direction. So what happens to these two equations if we plug in this value for acceleration and plug in that value for vertical acceleration, pardon me, horizontal component and vertical components of acceleration to both of these sets of equations? What do they look like and what do they simplify to? Well, you can actually, I recommend try pausing the lecture here for just a moment and do that and try and write out all three of these equations and all three of those equations, plugging in these values for a sub x and a sub y. Okay, now that you've done it, I hope that you have equations that look like this. And this is also summarized in our textbook in section 3.3 as well. So notice all of the x components of acceleration are 0. So the first and third equations just say the same thing. They just say that v sub x at all later times is equal to v sub x at launch, right, at the beginning. In other words, the horizontal component of the velocity is constant. It undergoes 0 acceleration. So it's the same at all times, at all later times as it is at launch. And then the horizontal position or displacement just proceeds like something that has constant velocity, which is exactly true. Our projectile has a constant horizontal component of velocity at all times. In the vertical direction, we have an object that is accelerating, and it's undergoing a constant acceleration of negative g at all times. So if we plug in negative g for all of these a sub y's, all three of these equations look pretty much the same. Okay, they look pretty much the same. The only difference is that now we've plugged in negative g for all of the accelerations. Okay, so these y equations look like something that's basically undergoing vertical free fall. Okay, this is just like the one-dimensional free fall equations that we used for something that was moving just up and down, directly up and down. Okay, so that these equations look exactly the same. All right, so we have an object that's moving horizontally at a constant speed and something that's moving vertically like it's in free fall. If we put all that together, this is what it looks like. So here at the top, I've just repeated those same two boxes of equations. So notice in the horizontal direction, this object's horizontal velocity component always has exactly the same number of meters per second at all times. So horizontally, if we were to look at the shadow of this little object along the ground as this projectile flies through the air, what would we see? We'd see the little shadow, if the sun were directly overhead, we'd see the shadow moving along at a constant horizontal velocity at all times. What about if what if we were to shine a really bright light on this object from the side and look at its shadow on a wall? What would we see? We would see an object that looks like it goes straight up in free fall and then falls straight back down in free fall. So the y component starts out with whatever the initial upward launch velocity is, and then it undergoes a negative acceleration at all times. So this initial positive velocity is shown here becomes more negative as time goes on. 9.8 meters per second, more negative every second that passes. Finally, all of that vertical velocity will be eaten away to zero right at the apex, right at the top of the trajectory. So there's no the vertical component of the velocity right up here at the top is zero. And then finally, the gravity doesn't stop there. Gravity keeps on accelerating it with negative 9.8 meters per second squared, negative 9.8 meters per second every second that passes until the object finally lands. So that means that the vertical component of the velocity starts becoming negative and more negative as time goes on until the object lands. And that's exactly what we see here. Now, this particular cartoon shows an object that is on level ground, and I'll say a little more about that in just a moment. But oh yes, okay. So I basically just said this, that if we look at the shadow on the wall here, we'd see that the object is basically, the motion of the shadow is identical to the motion of an object that's been thrown straight up. It slows down and slows down, pauses at the top of its arc momentarily, just for an instant, and then it falls straight back down, accelerating faster and faster until it lands. Okay. If we were to take, if we were to take this equation here for x, solve for t, and plug it into this equation number 2 here for y, and eliminate t, what we would wind up with is an equation for y in terms of x. And I've gone ahead and done that. And what we see is that y as a function of x it looks like it's quadratic in terms of x. It has a negative coefficient. These are constants. These are all constants right here on these two x coefficients. It has a negative coefficient on the x squared term, which means that this is a parabola with that faces downward. It opens downward, or it's concave down. Okay, so and that's exactly what we would expect for something that's in free fall. Here we have a parabola. So in fact, this path through space where we have y not as a function of time, but y as a function of x, okay? So vertical position as a function of horizontal position is always going to be a segment of a parabola. It will always be a section of a parabola. Okay? And we can prove that, and we've just sort of proven that to ourselves that mathematically it's exactly what it looks like. So as a negative term on the x coefficient right here. Now, I just want to say a little more about the special case of an object that is launched on horizontal ground. And you'll notice that because the parabola here is symmetrical, looks symmetrical from start to finish, that there are a lot of symmetries for this special case of level ground motion. The time of ascent is exactly equal to the time of descent, just as it was for an object that was thrown straight up and then caught back at the level from which it was thrown. However, if you launch a projectile from a cliff down to a lower level, or if you launch a projectile from a lower level up onto a ledge, then you can see that the time of ascent and time of descent are going to be unequal. They'll be asymmetrical, of course. Also, you can see that on either side of the apex of the peak, the we know that the horizontal component of velocity doesn't change. The vertical component of the velocity goes from being positive so many meters per second to negative the same number of meters per second. So what we can see is it looks like this velocity here, it looks like it's been flipped about the vertical axis, is all it looks like. So what that means is the total velocity of the object, meaning the total speed, will be the same, and the direction will have the same angle above the horizontal during ascent as it does below the horizontal during descent. So this is true on either side of the apex of the path. So that sort of symmetry is really handy. That lets us sort of answer a lot of questions very quickly about the motion of an object. Okay, if you know what the motion of the object is like at a certain position before the apex, then we essentially know everything just by inspection. We know everything about the motion of the object at the same position reflected on the other side of the apex just by symmetry. Right, speed is the same. Direction is just negative. It's just below the horizontal while during descent, above the horizontal during ascent. And the y component of velocity, the sign is just flipped. That's all. And the x component never changes. All right. Finally, let's just think about this vertical and horizontal relationship just a little bit more. Okay. Because if we were to ignore the horizontal motion, all we would have would be an object that looks like it's under free fall, just under, it looks like it's in one-dimensional vertical free fall. Then what that means is if we were to launch something horizontally, it would its shadow on the wall would look exactly the same as something that would be dropped straight down from rest. Okay? And indeed, that's exactly what we see. Okay? If we drop a ball and push a ball horizontally at exactly the same time, and then take a bunch of strobe photographs as they fall, notice how notice how the vertical motion of the object that is dropped from rest is exactly the same as the vertical motion of the object that is launched horizontally. Indeed, if we were to shine a bright light from the right so that the yellow ball casts a shadow onto a wall right here, then you could imagine that these red ball positions look exactly like the shadow spots that would be cast by the yellow ball. Okay, that's so the vertical motion is indistinguishable. There's a classic brain teaser that says if I were to fire a bullet from a gun horizontally at a very high speed, right, like 5 meters per second horizontally, and if I were to drop another bullet right next to it from rest at exactly the same moment as I fired the first bullet, which one would hit the ground first? Would the bullet that's fired out of the gun hit the ground first, or would the bullet that's dropped straight down hit the ground first? And the answer is they would both hit the ground at exactly the same time. Okay, they both have exactly the same y motion at all times. They have the same y acceleration, the same y velocity, and the same y positions at all times. This photo over here on the right just makes the extra point that whenever an object is in free fall, its path through space follows a section of a parabola. Now, notice the exact shape of the parabola, the exact sort of shape of the parabola, like how narrow or how tall it is, all depends on things like the initial launch direction and also how strong the gravity of the planet is. All of this assumes no air resistance, of course, right? But these are all parabolic. There's a really cool result that this is a classic sort of physics problem called the monkey. In the old days, it was called the monkey and hunter problem. And the question said that if you have a hunter here, and there's a monkey hanging up in a tree, and there's a hunter with a gun, and the hunter knows at the moment that he fires the gun, if you assume that sound travels instantly, the monkey will be startled by the sound of the gun, and the monkey will let go and start to fall from the tree. So if the hunter wanted to hit the monkey, let's say instead of with a bullet, let's say a tranquilizer dart to make it a little more kind to our animal friends, right? Then where should the hunter aim? Right? Should the hunter aim below the monkey, knowing that the monkey will fall and hit the bullet? Or should the hunter aim above the monkey so that the way the arc of the bullet will arc through the air and hit the monkey maybe somewhere up here, right? Where should he aim? Well, it turns out that gravity causes both objects to fall away from their zero gravity lines or zero gravity paths or positions by identical amounts of distance in identical amounts of time. In other words, their vertical displacements are exactly the same, just as they were in this photograph right here. Okay, so if there were no gravity, then at the moment, then what would happen to these two balls? You would release the red ball from rest, and it would simply stay put, and you would kick the yellow ball to the right, and it would just drift off in a straight line, right? At constant speed. Well, it turns out the same principle is the same if an object is launched at an angle too. Okay, if you were to shoot this arrow without any gravity being present, then the arrow would simply follow a straight line path. Okay, so in distant outer space, far away from any planet, the arrow would follow a straight line path. And the answer to where you should aim to hit the monkey would be obvious. You'd want to simply aim right at the monkey because when the monkey lets go, the monkey wouldn't fall either if there was no gravity. Now, if we turn gravity on, what will happen? It turns out that gravity will gradually displace the monkey below its starting point, and the monkey will fall faster and faster and faster. But gravity will displace the arrow away from its original path by the same amount in the same amount of time. So again, initially it'll just be a small displacement, but then it'll get bigger and bigger and bigger. And the arrow's vertical velocity will grow downward at the same rate as the monkey's vertical velocity grows downward as well. So it turns out that to ensure that the displacement of the the displacement of this arrow or tranquilizer dart below its original path is the same as the monkey, then we would need to just simply aim at the monkey at the start. And then they would both have fallen away by the same amount in the same amount of time from their original paths. There's a nice little derivation of this mathematically in the textbook. I decided I'm not going to show it here. It's just a cool problem with a cool result. And it's one of these classic problems that if you've taken introductory physics and introductory mechanics, people will expect you to probably have seen or heard of. So if you'd like to see the mathematical result for this, please take a look at section 3.3 of our textbook. There's another cool result that you can get from these equations as well. And that is also derived for us in 3.3 of our textbook in one of the example problems. And that is the question, what's the algebraic expression that tells us the range that this projectile will have traveled if this projectile is launched on level ground? What's the final range going to be? Now you can derive an expression for non-level ground. So again, if a projectile is launched from a cliff, right, of height h, or if it's launched up to a ledge of height h, and then the expression's more complicated. So we're not going to go into that. In our textbook, they just show the result for level ground. And the nice thing about the level ground result is it's relatively simple, right? The math sort of simplifies nicely. Okay, so if you solve for that, you can get a nice expression. And range, by the way, is a vocabulary term that I'd like you to know, right? It means the horizontal displacement of an object. If it usually implies final, so when we ask what's the range of the projectile, it usually means from launch to landing. Although you could also just say, what is the range of the projectile at any moment along its path, in which case we simply mean the intermediate horizontal displacement. So sometimes in our textbook, you'll see it used that way as well. Okay, so range is a synonym for horizontal displacement. All right, now take a look at this equation. Okay, this is the launch speed. So this is the total meters per second at launch, not either one of the components, but the entire muzzle speed, nozzle speed, right? The entire launch speed. That's v naught, v sub 0. And then this is the launch angle above the horizontal, right? And this is for above the horizontal. And notice that it's doubled. So the angle is doubled here in this sign. All right. Now, what I'd like you to think about is suppose we have some sort of a cannon or some sort of launch device that only launches at one speed only. Okay, so we can't change the speed, but we can change the angle at which we launch an object. What angle should we choose to launch something at so that it will land at the greatest possible range? Okay, common sense would tell us if we launch it really high, then the range might not be very big. The object will go way up and come back down relatively nearby. Common sense also tells us that if we launch really low, then the object's not in the air for very long, right? It will just sort of skim the ground quickly and launch and land soon. So there must be some sort of an angle in between at which we would get a really, really big range. And the question I want to know is, what is that angle? So if you would, pause the lecture for a moment and try and figure out what is the value of theta naught, right, the launch direction, so that the value of r will be maximized, knowing that g and v naught are constant. Okay, I hope that you were able to figure out, okay, in order for r to be maximized, if v naught and g are constant, we need this sine function here to be maximized. Well, the biggest value that sine can have is what? It's 1, right? Well, sine has a value of 1 when the argument has a value of 90 degrees. When this is 90 degrees in the argument that we're using for sine, then that means theta naught must be 45 degrees. So 45 times 2 will be 90. So it turns out that this angle right here, to maximize the range, if this cartoon were to show the maximum range, then the launch angle right here of the blue path, of the blue dashed path, would be 45 degrees. That's something that I recommend you just memorize. That's just it's a really, really handy result. Okay. Now, again, I want to remind you this is for zero air resistance. Okay, air resistance will mess that up a little bit, and we'll see a demonstration of that in just a minute. Also, what happens if you plug in 90 degrees for the launch angle? So in other words, if you launch something straight up, what does the range become? Well, the range becomes V naught squared times sine of 2 times 90, which is sine of 180. And what's the sine of 180 degrees? Yeah, it's 0, right? So that makes a lot of sense. That gives us confidence that this formula is correct. Something that's launched at 90 degrees is just going to go straight up and come right back down and hit you back in the head. If something's launched at 0 degrees, then it can't go anywhere before it just stops because it hits the ground right away. So again, its range would be 0 as well. Okay, so launching at 90 or at 0 gives you a range of nothing. Launching at 45, halfway in between those, gives you the maximum possible value for the range. And the last thing I would like you to notice is let's suppose the maximum range over here, right, is way over here. We'll call that R max. What angle should we launch something at to get it to land somewhere closer than R max, but not a 0, right? So maybe at 1/2 of R max or 1/3 of R max or something like that. Well, it turns out if we plug in any value of R here for the range that is smaller than R max, and then we solve for theta and solve for theta 0, theta naught, to find out what's the value of theta naught that will give us that particular range R. There are two answers, right? When we take the inverse sine to solve for theta naught, inverse sine has two solutions between 0 and 180 degrees. Right? Remember that every inverse trig function has two solutions on the unit circle, and it turns out for sine, between both of those solutions are going to be between 0 and 180, right? Or if we limit our, yes, for positive values, right? For when we do the inverse sine of a positive value, both of those solutions are going to be between 0 and 180, which is what all these quantities here are positive. Okay. So that means it's going to be 2 theta is going to be equal to two different values between 0 and 180. And then if we divide both those values through by 2, then we get two possible values between 0 and 90. So it turns out, what are those two possible angles then? There are two solutions. There are two solutions. To achieve any of these ranges in here that are smaller than R max, you can either launch at a low theta, or we could launch at 90 minus that low theta at this high theta. And in both of those cases, they'll both land at exactly the same range. Notice that the time of flight is very different for both of these. The maximum height reached is very different for both of these. Okay, this is a very short time of flight, and that's a very long time of flight. But the landing point is exactly the same for both. Okay, and we'll see a little demonstration of that as well. All right, finally, we're not going to learn any equations for what the path of a projectile is when you add air resistance or air drag. But because it's such a common real life situation, I mean, it's a little bit artificial for us to keep saying, assume no air resistance, assume no air resistance. If you do add air drag, and this is a pretty dramatic example here, okay? So this would be for an object with a moderately high either coefficient of drag or a relatively large diameter of the object, so that way it catches a lot of air, right? It has to interact with a lot of air. And this is generally true for any fluid as well, but um, then what happens to the path, okay? So this is showing the path y versus x through space. Without air drag is this paler path over here, right? Notice that's our perfect parabola, okay? Notice that as we add air drag, right, then three things happen. First of all, the total range will get reduced. And that's because and the second thing that happens is that the maximum height also gets reduced. Okay, and that both of those are because air drag acts opposite to the direction of motion. So as the direction of motion of this object is in both the x and y directions, then air drag exerts a force or a negative acceleration that is both in the negative x direction, thereby slowing down the x velocity and causing it to land closer, and in the y direction, thereby slowing down the y velocity, causing it to not get as high. Also, by slowing down the y velocity, we shorten the total time of flight as well. So I guess I could have added that to this slide as well. The time of flight is greatly reduced. Also, there's a subtle effect that's a little hard to see on this slide, but if you sort of look at the slide from the edge and squint a little, what you'll notice is the parabola is no longer symmetrical. It looks like it's been squished a little from the right side. So there's a skew now to the parabola, right? As opposed to the airless case where the parabola is perfectly symmetrical about its apex. Now you can see that the apex is offset to the right. Okay, the right side of this sort of quasi parabola here, this non-parabola, the right side is steeper, and the left side is more curved. Okay? So the parabola becomes asymmetrical when you add air drag. I'm going to now switch over to a simulation. This is one of the many physics and other science simulations that are available online from the University of Colorado. So if you use the slides, if you look at the PDF file of our lecture slides, then you can click on this link instead of having to type the whole thing in, and it'll take you directly there. Or you can just do a Google, you can just Google PHET University of Colorado, or go to phet.colorado.edu. You'll have to click through a few more things to get to the physics simulations, and then look for the one on projectile motion. What I recommend that you try is some of you can just mess around with this. You can change every possible parameter having to do with this objects, and I recommend that you try a few different things. And try adjusting the air drag. You can turn it off, turn it on, make it light, make it heavy. You can also change the launch angle and find out what the range is going to be in each case. And you can change many other aspects. So let's switch over to projectile motion right now, to the app. Okay, good. All right, so this is what the app looks like when you first get there. Um, all four of these things take you to the same general app. All that changes is a couple of the things over here on the upper right. So these little options here change depending on whether you chose intro, vectors, drag, or laboratory. Okay, so but otherwise, it pretty much all functions the same way. You can grab the launcher and move it up and down. You can grab the launcher and change the launch angle. Okay, and you can vary other things about the projectile. So I'd like to show you four things related to everything that we just covered in the theory slides as sort of a little animated demonstration of those things. So first of all, I'm going to set the initial speed to a medium value, so that way the object's entire trajectory will be visible on the screen. And um, I've set it so it's a small cannonball. Okay, great. All right, wonderful. So there we have our parabola. That's our parabolic path. Just so you know, it uses actual real numerical values. So gravity is set to negative 9.8 in the y direction. The little small dots here are every 10th of a second, and the larger dots are every whole second. So this is 1.0 seconds, 2.0 seconds, and so on. The little green dot here shows you where the apex of the path is. All right. Now, one of the first things to notice is, again, the parabolic shape. Yes, excellent. And the other thing to notice is what the velocity vectors are doing. I'm going to slow this down into slow-mo a little bit, and let's look at that again. Notice the horizontal component of the velocity first. Okay, the horizontal component never ever changes. It has the same value the entire time. The vertical component started very large, gets more negative, more negative, more negative, more negative, more negative at all times. Right? In specifically, it becomes 9.8 meters per second more negative for every second that passes. Let's look at that one more time. The vertical component of the velocity at the very top goes to 0. So the vertical component goes to 0. The horizontal component has never changed. It still has plenty of speed in the horizontal direction. In fact, the exact same speed it had before, and will have at all later times as well. Okay, so that's how we know mathematically that we're at the apex. V sub y is equal to 0. The vertical component of the velocity is equal to 0. Notice at any time, we don't have any equations that tell us what the total instantaneous velocity component, or the instantaneous velocity magnitude and direction are. Right? We know what the components are from all of our horizontal component equations and vertical component equations. So if I ask you, what is the total velocity at time t equal to 2.5 seconds? Or what is the total velocity, magnitude, and direction at landing? What you have to do is you have to find what the horizontal component is at 2.5 seconds or at landing. And then you need to separately find what the vertical component is at your desired time or at landing. Then put those two together to get the total magnitude, and take the inverse tangent of those two to get the trig direction. Okay, so that's what you have to do to find the magnitude or direction of velocity at any later time. Notice that this animation is showing us at all moments here. This animation is doing the component recombination for us. And you can see that the magnitude here, right? If you add X component to Y component, that's the magnitude, and then there's the direction right there. And let's watch that one more time. You can see, okay, so notice that at all moments during ascent, the total velocity, here's the X component, there's the Y component, so that's the total velocity magnitude or speed, and this is the total velocity direction. Okay. Notice it's also always tangent to the path. So the path, of course, is the blue parabola, and the total velocity is always tangent to the path at all moments. Right? That's always true for vectors. Okay. I just like seeing the stars when it hits the bullseye. All right. So what I'd like to do now is part 2 of my 4-part demonstration here is to try varying the range, varying the launch angle and see if we can verify where the maximum range occurs. Okay. So unfortunately, it will only show 5 paths at a time before it starts to erase them. So what I'm going to do is I'm going to vary the launch angle by fairly big chunks, by 10 degrees at a time. So let's start with 65 degrees. Okay. Okay, actually, what I'm going to do, I got to speed this back up, pardon me, and I got to clear it as well. Okay, so let's start with 65 degrees. And we'll see where it lands. Boom, there we go. Okay, so that's the range right now. Unfortunately, it's not saying anywhere over here what that range is numerically, but we can just see visually, we can see what the range is right now, somewhere beyond 15 meters. Now let's change the launch angle to 55 degrees. Do you think the range is going to increase or decrease? Right. If you remember where we expect the maximum range to occur, I'm getting closer to where we would get the maximum range. Now let's change 45 degrees. Boom, here we go. Right, even farther away from the launch point. If I switch to 35 degrees, should it go farther? No, 45 degrees is the angle at which we expect maximum range to be reached for an object with no air resistance. Okay. Now notice something interesting happened. Is that just a coincidence that 35 degrees landed at the same place as 55 degrees at the same range? No, it's not a coincidence. In fact, if you remember, here, let's go to 25 degrees. Right? Notice how 25 degrees landed at the same final range as 65 degrees did. Right? Remember, when you launch at theta or at 90 minus theta, the final range on level ground will be the same. I want to emphasize that equation was for level ground only. Okay, I can't emphasize that enough. So you have to remember what the assumptions are. That's not a fundamental equation of physics. That's a special result that's derived for level ground only. So always be aware of that when if you're going to use that equation, you have to be aware of that assumption. All right, so there we go. And it turns out if we were to launch at any other pair of angles that are complementary to each other. So if I were to launch at 30 degrees, it would land at the same location as if I launched at 60 degrees. Or if I were to launch at 41 degrees and 49 degrees, it would land at the same location as well. Let's just quickly look at the time of flight, and you can tell by these sort of little dots that are along the path. Notice that the time of flight for 25 degrees is a little over 1 second, so about 1.3 seconds. But the time of flight for 65 degrees looks like it was 1, 2, not quite 3 seconds, right? So about 2.7 seconds or so. So 1.3 seconds versus like 2.7 seconds, dramatically different, right? Yeah. So the time of flight and of course the maximum height reached, dramatically different as well. Okay. All right. So I encourage you to sort of mess around with this. If we launch at, unfortunately, this launcher doesn't go below 25 at this point. You can do that if you raise it up, but I don't want to raise it up. I want to leave it right at ground level. Okay. If we launch straight up, what will the range be? Yep, the range will be 0. Boom. All right, good. All right, so the third thing I'd like to investigate is I'm going to go over to the vectors tab here. And the only reason I'm switching tabs now to the vectors tab is because this will give me different options over here in the upper right. So the third thing I'd like to investigate is how does the path of this projectile vary with mass? So let's start with a low mass projectile, just 2 kilograms, and we'll launch it and see where it lands. Okay, or actually look at the whole path, right? So there's the whole path. There's the final range, everything, great. Let's make the projectile more massive. Let's triple the mass. We'll make it 6 kilograms. Now I'm going to visually triple the diameter just so it looks bigger to us as well, right? Um, but you know, that's the diameter is not the same thing as mass, of course. The two don't scale. The two don't scale with each other, especially if you keep the object's density the same, right? All right. I just want it to visually look bigger on the screen. Let me ask you to predict. I've just tripled the mass of this cannonball. Before I launch it, how will the path change? Will it land closer? Will it land farther? Will it go not less high? Will it go, even higher? All right, let's find out. Behold, it's exactly the same, right? Think about our equations for projectile motion. Does mass ever appear in any of them? No, it does not. Okay, and indeed, here let's go to the biggest, the maximum mass, and we'll make it visually bigger too. Boom. So there we have a monster cannonball, exactly the same path. So when there's no air resistance, now if you do increase the mass of an object, then it plows through the air a little better. It has more inertia. And if you increase the diameter of an object, then it encounters more air resistance. So the air pushes back on it. So if we turn on air resistance, then these two factors here will matter. But in an airless situation where we have zero air drag, zero air resistance, our equations for kinematics for projectile motion are mass independent, just as they were for free fall. Do you remember that? For the law of falling bodies, the mass of the object that was being thrown or dropped it doesn't enter any of the equations, and the acceleration of the object, velocity, position, etc., displacement, is independent of the mass. Okay, that was part of Galileo's great discoveries with his law of falling bodies. Then the last thing, part 4, that I'd like to investigate here is what happens with or without air resistance. Okay, so what I'm going to do is I'm just going to sort of put our cannonball back at a smaller mass here. Actually, I'll leave the cannonball big, so visually it's still easy for you to see. This blue path right here is a path that it has without any air drag or without any air resistance. Now I'm going to turn on the air drag. They don't let me adjust the sort of viscosity of the air or the drag coefficient of the object, right? They've sort of left it fixed. That's fine. That's great. This is a moderate, we'll just assume this is a moderate amount of air drag, air resistance. And now the path that it's going to trace out is going to be shown in purple instead of in blue. Now, do you remember from the last slide that we looked at, how will the path differ? So think about that for a sec. All right, and then we'll launch it and see. Ready? All right, so notice a lot of like the total range is greatly reduced, maximum height greatly reduced. The time of flight as a result, therefore, also is shortened, right? This is like 2.3 seconds, and this one didn't quite make it to 2 seconds. And if you look really carefully, you'll notice that the parabola is sort of squashed a little bit from the right side. It's been distorted, so it's skewed, right? It's not symmetrical anymore about the center or the apex, which is the green dot up there. What I'm going to do is I'm going to make the air resistance a little more dramatic by decreasing the mass of the object, but leaving the diameter really big. So in other words, I'm making the object out of a fluffier substance, right? So before it might have been made out of lead, but then it was made out of wood or lead. Now we're making it out of wood, and then I'll make it out of styrofoam, and we'll see what happens, okay? So now you can see all of the effects of air drag are becoming more and more dramatic. And then finally, I can make the mass very low, but leave the diameter huge. So this is like a beach ball, basically, right? So, the drag on the beach ball is extremely large, right? Now you can really see the asymmetry in the parabola. Now it becomes a little more obvious, but also all those other effects just become more and more dramatic, right? So you can accomplish the same effect by making the air thicker and gooier, for example, right? All of these same things will happen again. Going back, actually, what I wanted to quickly do is go back to this first air drag case and turn on the velocity vectors. And let's slow down time a little bit, and we'll launch this first air drag case. Notice what's happening here to the horizontal velocity vector? Well, actually, it's a little subtle. Let's make the air drag a little more dramatic. So let's go to this second case again. Okay, watch what's happening to this horizontal velocity vector. Notice in this case, it's shrinking and it's getting smaller and smaller and smaller, right? That's not something that happens when we take the air away. When you take the air away, horizontal velocity is a constant at all times because gravity doesn't act in the horizontal direction and there are no other forces acting on the object when it's airless, right? But if we turn the air resistance on, then the horizontal component of the velocity decreases and decreases. And that's why the range is so much greatly reduced, right? In the case of something with air drag. All right. So when you want to launch something, um, when you want to launch something and hit a target, like we do, for example, in the military, if you want to hit something with a tank mortar or something, then you have to, of course, do the calculations with air drag. So these calculations are actually, you can't solve these equations analytically just with pencil and paper. They have to be solved numerically. You have to calculate one time step and then recalculate the forces and then calculate another time step and recalculate the forces and so on. So these can be done with a computer pretty easily. In the old days, I guess they had lookup tables and charts where people had pre-calculated the necessary launch angles for different situations with air drag. Okay. All right. Also, what we can do is quickly investigate where the maximum range is achieved. So what I'm going to do is I'm going to leave sort of a medium amount of air drag on. Okay, we'll do that. And but I'm going to increase the speed of the object just so we can make a bigger path here. Okay, so right now we're at 50 degrees. Okay, so well, actually, you know what? Let's start down here at the lower angle. Okay, all right. So 20 meters per second, or 25, pardon me, 25 degrees. Okay. All right. Oh, I can speed it back up. Okay. So, all right, actually, you know what? Let me reset this one more time. All right. So what we're going to do is, this is the last thing we're going to do with the air drag on. We're going to try and investigate if we can find out at what launch angle we would get the maximum range. So we know that without air, the maximum range is achieved at a launch angle of 45, right? Let's start here at 55 and step through and see if when we add air drag, where the maximum launch angle is achieved. Okay, great. So I'm sorry, the maximum range is achieved at what launch angle? All right, so all right, notice that here's the range at 55 degrees. Let's go to 50 degrees, launch again. Okay, the range is a little bigger. All right, good. And let's go to 45 degrees. All right. Now, in the case of no air, we would know that that would be the maximum range. However, if I go past that to 40 degrees, let's see what happens. Notice the range actually just got a little bigger. It's hard to tell here, but at 40 degrees, the range actually has increased. So in the airless case, the range would have dropped back to something less, but 40 degrees actually lets us get out even further. And then finally, if we go to 35 degrees, I suspect we will have passed our maximum. Yep. So now finally at 35 degrees, it's dropping back. So the maximum range for this particular combination of drag coefficient and everything else and is somewhere around 40 degrees, not 45. Okay. Probably plus or minus a little bit, maybe 41 degrees, maybe 39, something out there. Okay. All right. So this is known. This is a known thing. And the reason is because when you launch something with air resistance present, it helps to have more velocity in the horizontal direction to counteract the drag that happens in the horizontal direction. So to help push against that drag a little bit extra, it helps to have a little extra horizontal velocity, right? And that will help you to get a larger range. All right. So what I'd like to do now is that 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 concludes all of the uh, slides I wanted to show you and all of the demos I wanted to do. So what I'm going to do now is switch to doing some sample problems. So at this point, I'm going to solve problem number 1 and problem number 4. Problem number 1 and problem number 4 from tutorial number 11. Okay. So if you like, you can stop the lecture now and just look at my written solutions that are already uploaded, or just go ahead and try the online problems at this point. Okay. Now, I'm going to switch. It'll be easier for us with these more complex equations and everything if I do this on pen and paper. So let's switch to pen and paper now. Okay, so here's tutorial number 11. All right, and the first thing that this is asking us is to, problem number 1 is about a level ground problem. Again, a soccer ball that's on a level field is kicked from the ground at an angle of 30 degrees above the horizontal at an initial speed of 20 meters per second. Now, looking ahead, initially there's a bunch of quick sort of almost conceptual questions that require minimal calculation. And then later, we're asked some problems that most definitely require calculation and a calculator, right? Like what's the maximum height that the soccer ball achieves? What's the final horizontal displacement, right? In other words, the final range, and so on, okay? And then there are some little graphs that we're asked to generate for the horizontal position, velocity, and acceleration as functions of time, and the same for the vertical direction. Now, first what I'm going to do, though, is I'm going to spend a little time for this particular problem visualizing what's going on with the motion of the ball, okay? So this is just to reinforce what we saw already in those previous drawings and what we saw during the demonstration, the applet demonstration. Okay, first of all, let's ask ourselves, what does the horizontal, so here's some little snapshots taken of the ball, okay, at equally spaced times, right? What does the horizontal component of the ball's velocity do over time? Well, if you remember correctly, acceleration does not act in the horizontal direction. So there is 0 acceleration, which means constant velocity. So at all later times, we would expect the magnitude of the velocity vector to be exactly equal to what it is here at the start, right? So I'm going to try and draw a horizontal component of the velocity that's exactly the same length at all later times. Okay? So that's Vx at all later times. Got to make that look like an X. Okay. In this case, I want to move my little label. Okay. Now, what about the y component of the velocity? What's that going to do as time passes for this projectile, for this soccer ball? Well, remember the y component of velocity is becoming more negative with every passing second. Okay, so it starts out with this large positive quantity, which we'll calculate in just a moment. And then as time goes on, that's going to become more negative. Do I know, has it already become negative yet? No. Remember, it reaches 0 here at the apex at the top. So I want to sort of pace myself here. It's becoming more negative, meaning less positive as time goes on, and less positive, even smaller, and then 0 right up here at the top. So here's the y components. And then here at the top, the y component is 0. And then if I remember symmetry about the apex, then I should draw a y component that's about the same size, only negative on the way when it's on the way down. And then the same size, only negative when it's on the way down. And then finally here, because this is level ground, the symmetry continues all the way to landing. Right? So here is the y component right at landing. All right. So what does the total velocity of this soccer ball look like at each of those moments in time? Okay. Well, again, if we move the y component over and add the y component to the tip of the x component, or vice versa, add the x component to the tip of the y component, then what do we get? We get a total velocity vector that looks like this, right? and then a total velocity vector that looks like that. So that's the total, the whole velocity vector, the whole velocity, the magnitude of that whole vector there is the speed, right? At the very top, there is no y component, right? The y component is momentarily 0. That's how we know we're at the apex. But the x component is still very much present. So that means that the total speed, the total velocity is the speed, I should say, the magnitude of the total velocity is just equal to the x component only, right? So those two are exactly the same. There is only an x component, put another way, right? What do you think is happening here while I finish the rest of this? What do you think is happening to the direction of this velocity vector as it descends? And then finally here, one thing we could do is we could call this V naught here at launch, and then sometimes at landing, I'll call it V final, which means that's it. That's the final, right? These other velocities, if we really wanted to, we could label these perhaps with their times, V1, V2, V3, or something like that. This could be V peak if you wanted, and then this could be V final because it really is at the end. So this would be V final Y and V final X. Okay. All right. Notice here, this was theta naught, theta, theta. Theta here is equal to 0. And now theta here is negative, right? So if we follow our trig convention, if we go clockwise from the positive x direction, then the value of theta is negative, and this is theta final, and the value of theta final will be negative, right? There's symmetry here. So at an equal time after the peak, theta has the same magnitude as it did at that same time before the peak, only it's negative instead of positive. That's the only difference, right? Same thing with the y components, negative instead of positive. So on level ground, theta final is the same number of degrees below the horizontal as theta initial was, right? It's only just negative, right? Negative for trig angle or below the horizontal in English. What about the final speed? What about the speed at landing? Again, by symmetry, we can see that whatever the speed at launch is, which is 20 meters per second, then the speed at landing will also be 20 meters per second because we are on level ground. I want to emphasize, because we're on level ground, the symmetry holds about the center of the parabola. So for the same number of seconds before as after the center of the parabola, that symmetry holds. If we were launching from up high up on a cliff to lower ground, then this part of the parabola would be symmetric, then the remainder would have no corresponding part on beforehand. Okay, so it would not be correct if we launched from a high cliff at 20 meters per second. It would not be correct to say that the ball lands at a lower level at 20 meters per second. No, it would land fast. And the reverse is true if we were launched from a low point up onto a ledge. Then the total speed of landing would be slower. A lot of this is pretty common sense, right? This makes sense with what we know from daily life, right? We throw lots of projectiles all the time, so and we have a lot of experience with them. All right. Now, for almost every projectile motion problem that I work on, it is going to be desirable for us to know the x and y components of the initial velocity. Notice how all of these horizontal component equations all have the x component of the initial velocity, and all three of the vertical component equations have the y component of initial velocity. So if what we're given is the initial velocity, magnitude, and direction, right? So that's theta naught and that's V naught. Then what we should do is we should calculate what V naught X is and what V naught Y is. So that's exactly what this is asking for. But notice here, I'm just sort of setting you up by being explicit about it. For all future projectile motion problems, I'm not going to ask for that, but I recommend that you calculate it as your first step, because that way you'll be all set to plug it into these values. The only exception when you can't do that is a problem when you're not given either the initial launch direction or the initial launch speed. But those tend to be harder problems, right? And sometimes in those cases, you can use that range formula that we already derived. Okay? Most of the easy or intermediate projectile problems are going to give you the initial launch direction and the initial launch speed, and you can then use that to find v naught x and v naught y. So let's go ahead and do that. Okay. Remember, if we know the magnitude and direction, then the way we get the x component is magnitude times cosine of the angle. And the way we would get the y component is magnitude times sine of the initial angle. So plugging in, turns out that this is approximately 17.3 meters per second. Okay. It's about 17.32. That might be useful for us. That extra sig fig might be useful for us in some later calculations. But if this were a final answer, then I would stop at 17.3. And this is exact, right? Sine of 30 degrees is exactly 1/2. All right. So now we know what V naught is in components. Okay. Put another way, V naught is equal to 17.32 meters per second, comma 10 meters per second. Okay. Or we could use I hat, J hat notation or X hat, Y hat. At the highest point, now these questions, the following questions here are actually ones that require no further calculation. Okay, these next three. At the highest point of the ball's trajectory, what's the horizontal component of the ball's velocity? All right, well, we've already established that the horizontal component never changes after launch. The entire time of flight, the horizontal component Vx is always constant. So we know that at all times, Vx is simply equal to V naught x. In fact, that's what that first equation, the first of our equations of kinematics, that's what it becomes. If we plug in 0 for a sub x here, then Vx is equal to V naught x at all later times if there's no acceleration, right? If we just cover that right there. Yep, so then that just becomes true at all later times. Right? So that's going to be equal to 17.3 meters per second. And that includes at the highest point. It also includes right before the landing. Right? At the highest point, what's the vertical component of the ball's velocity? Well, by definition, how do we know we're at the highest point or the apex? It's when the vertical component is momentarily 0, right? That's when the vertical component of the y velocity is turning around from being positive to negative. Right at that apex right up there is when it's equal to 0. So that's how we know we're at the apex. Then finally, what's the total final velocity vector right before landing? Now, I remind you here, use the symmetry of the soccer ball's path, okay? Because this is a level ground problem. So we know that the soccer ball was launched at 20 meters per second speed, 30 degrees above the horizontal, right? So right at landing, we'd expect the speed to also be, let's look at the diagram. 20 meters per second here, 30 degrees above the horizontal at launch. So right at landing, we'd expect it to also be 20 meters per second, 30 degrees below the horizontal, just by symmetry. Okay, so that looks like D. You can do a lot of calculation and prove that to yourself, but the nice thing is just from the symmetry of the parabola, we could just do that directly. All right, let's take a look now at the remaining parts that do require a little more calculation. Now, I want to emphasize that there are often going to be more than one way to use our equations of kinematics here to get to the desired answers, right? So I'm going to show you one way that I think is probably fairly quick and fairly efficient, but there is, if you chose to use different equations in a different order, you'll still get to the same answer. You can still get to the same answer, and that is also correct. All right, so how much time is the ball in the air? All right, well, in other words, that's asking what is the time at landing, right? Well, there's two ways for us to approach this, right? One is the way that you would do for non-level ground, which is to say, okay, when y equals when y equals the value it's going to have at landing, okay, or when delta y reaches the value it's going to have at landing, then then solve for t. Okay, what's the value of t at that moment, right? And that is the classic way to do it. So that's a way we can use if we want. There's another way that we could do it in this particular case, and it builds on the fact that this particular problem uses level ground, and that is you could solve for the time it takes to get to the peak, solve for that amount of time, and then double it, because we know that the time of ascent and time of descent are symmetrical about the center of the parabola, right? That would also be a valid approach. So I'm not going to show that at this moment, just in the interest of time. Okay, but that would also work. Okay, so we're going to find t when we have a choice. We can either say when y final is equal to y initial, right? That would be, and we could set those both equal to 0 if we decided to define our origin right here at the ground, like that. Or we could also say, or when delta y is equal to 0, which means that the soccer ball's vertical displacement has returned back to its starting position. In other words, soccer ball has returned back to its starting vertical position. So its vertical displacement at that moment is 0. Again, only true for level ground in that case. All right. So in that case, let's use our equation number 2 here for vertical components. Okay. Now again, we're going to say, okay, we can either say that these two are equal, or we could subtract and say delta y is equal to 0, or we can just say, you know what, they're both at 0. Okay. So at y final, right, minus 1/2 g t final squared. All right, great. Now if I solve for t, let me solve it algebraically first. T final, it looks like t final is going to be equal to 2 v naught y over g. Okay, so I don't need the quadratic formula in this case. One of the powers of t cancels out. And let's go ahead and calculate what that is. 2 times v naught y from up here. We found it already. So I just keep that handy. And we'll divide by g, 9.8 meters per second squared. Sorry, I'm starting to run out of room a little bit here. And then I asked my calculator what that is. My calculator says it's about 2.041 seconds. And that might, 2 sig figs, it rounds off to 2.04 seconds. All right, so that's the total time of flight. At this point, if I wanted to know what's the time it takes to get to the peak, I could just exactly take half of that, because again, this is level ground. So therefore, there's total symmetry about the apex, the peak of the parabola. If this were not level ground, it wouldn't be that simple. What's the maximum height above the field that the ball achieves? Okay, again, lots of ways to get to that. What I think I'm going to use is I'm going to use the fact that at the peak, okay, by definition, at the peak, the y component of the velocity is 0. That's how we know we are at the peak. So that means I can use this equation 3 right here to solve for the vertical displacement at the peak where I know the vertical component of the velocity. And everything else is known. Everything else we've already calculated. So therefore, I can use equation 3, Vy at the peak squared is equal to V naught y squared, which is this 10 meters per second, plus 2 negative g delta y at the peak. Okay. There's a lot of correct ways to proceed at this point. This is 0, 10 meters per second squared, plus 2 times negative 9.8. And then I can solve and find that the vertical displacement at the peak is 5.102 meters rounding to 2 sig figs, 5.10. Okay, finally, how do we get the range? This is actually one of the easiest things to sort of approach because there's only one equation that has range in it, and it's equation number 2 for the horizontal components. There it is right there. So if we say that we start at the origin, then we could say what's x final. Or if we don't know what our starting position is, we could say what's delta x at the final time. Okay. Why don't we go ahead and define this as the origin here? Let's define x naught as equal to 0. Okay. So then we can say, all right, x final is equal to x naught plus v naught xt plus 1/2 at squared. And this is time at landing, right? Notice that we need to know what the time is at landing. So if we hadn't already found it for part F right here, then we would have to calculate it. Otherwise, there's no other equation that allows us to get to the final range, right? Remember the fact that we can't use this equation 3 here because these accelerations here are all 0 in the horizontal direction. So let me go ahead and plug that in. Horizontal acceleration is 0. Okay. Luckily, we already do know the time at landing because we found that in part F. So final position, if we start at an initial position of 0, is equal to v naught x times t final. Let me just rewrite that again so it's really clear. 17.32, 2.041. I'm adding back in that extra sig fig just to help prevent round off errors. And my calculator tells me that the answer is 35.31 meters. Now I'll round off to the 3 sig figs. All right. Let's quickly construct these graphs down here. Now, you know what? I'm going to, without looking at any of the initial values up above, just knowing that we're dealing with a projectile on level ground, okay? So knowing that we have a projectile that has some sort of upward launch and upward launch angle, and it's going to land back on level ground, meaning it's going to land back at the same sort of vertical position at which it started. Then we know there's a lot of symmetries there, right? We already know there's a lot of symmetries with the velocities, right? Like, for example, the final y velocity is just the negative of the initial y velocity. Can I sketch what all these graphs should look like qualitatively without even labeling any of the values? Well, my advice is, as with all of our kinematics graphs that we've done before, start with the acceleration graphs because those are going to be the simplest, right? We know that all of these problems are constant acceleration. And then let's move to the velocity graphs, and then we'll move to the position graphs. Okay. So we can do the horizontal. Let's do the horizontal stuff first. What is the value of the horizontal component of acceleration at all times? Right. Gravity doesn't, when an object is in free fall, there should be no horizontal force acting on it. Gravity acts vertically. So therefore, this should just be, let's call this the landing here, 2.0 seconds. You know what? I won't even bother putting the actual numerical values in. We'll just call this T5. Okay. So there we go, right? It's just 0. Now, what does the velocity of the object do? The horizontal component of the velocity, right? These are all horizontal components here. What does the horizontal component velocity of the soccer ball do over time? Well, it starts out at some initial value, and it maintains that initial value at all later times, right? It's completely constant. Is that consistent with an acceleration of 0? Yes. Right? So here's landing. So this is just v naught x, whatever that value is. In this case, it's 17.3 meters per second. Right? All right, that's it. Yep, and acceleration is the slope of the velocity graph. Good, perfect. Now, what should the horizontal position of the soccer ball do over time? Well, that, right, common sense tells us that the horizontal position of the soccer ball increases sort of monotonically, right, at all later times. How does it increase? Well, here, we'll start at the origin. We'll assume that the origin is where the ball is kicked from, okay? And then it increases in such a manner so that the velocity is the slope of the position graph. Well, the velocity has one constant positive value at all times, so therefore we should want to draw a position graph that has one constant positive slope at all times. And that's what we should do. And this is landing right here. So that would be x final, right? That's the max, that's the total range that's achieved. So the ball progresses down from downrange, downrange, downrange at a steady rate of 17.3 meters per second until finally it lands at 35 meters. How about the y component graphs? So what is the y component of the acceleration? Well, we know that is provided by gravity. So its value is going to always be in the negative y direction toward the center of the Earth. So this value here is negative g. Okay. How about the y component of velocity? All right. So again, just looking at my little cartoon here, the y component of velocity starts positive in this case, right? The ball is launched upward from the ground. It gets less positive, less positive, less positive, reaches zero mid-flight, then becomes more negative, more negative, more negative until landing. It has its greatest negative value. So if this is landing here, and this is mid-flight right there, and it starts out here with this initial positive value, then we'd expect at mid-flight, we'd expect it to be zero. And then at landing, we know from symmetry that it should also be at the negative, right? We know that v final y is equal to negative v initial y, just because of the symmetry of this of level ground, right? What's the relationship again between acceleration and velocity graphs? Acceleration is the slope of the velocity graph. So notice the slope, acceleration is a constant negative value. The slope of the velocity graph is a constant negative value. Good. Finally, what is the y position doing over time? Well, let's again define the ball was kicked at the origin. So we'll say the initial y position is zero. We know because of level ground that the final y position is also zero. And halfway through flight, the y position reaches some sort of maximum. So we'd say at landing, the y position will be zero. At launch, the y position is at zero. And halfway through, right, so this is also 1/2 t final. Halfway through, the y position reaches some sort of maximum value. Now, this y-axis does not have the same scale as that one. This is 35 meters. This is only going to be 5.1 meters, right? So this is y max. I'm just enlarging it to make it more dramatic here. Not the best artist. Okay. Now, let's double check one more time. Okay. First of all, does velocity at all times should be the slope of the position graph, right? So we have a large positive slope, yes. Decreasing positive slope, yes. Zero slope, right at this time, right, at 1/2 t final. Increasing negative slope, yes. Largest negative slope, yes. Good. Okay, so that's exactly what we would expect. Also, does it stand to reason that this, I mean, what shape is this exactly, right? It looks like it might be a parabola, but is it a parabola? Well, let's look at our equations. And we can see that y, in fact, does depend on negative, it's 1/2 times negative g. So negative constant times t squared. So if I have a graph of y versus t squared, I'd expect it to be a parabola. Looks like it's a quadratic with a negative coefficient on the t squared term. So therefore, it's a downward opening parabola. Yeah, that's exactly right. Okay, so that's exactly what this is. This is a downward opening parabola. Good. And if you want now, you can decorate these with all of the other numerical values that we've calculated in the previous parts of the problem. But that's fine. This at least gives us the qualitative shapes. All right, let's move on to problem number 4. Now, problem number 4 doesn't have nearly as many individual parts, but it leaves, so problems 2, 3, and 4 leave a lot more up to you to decide how to do, or which of these intermediate values to calculate, in what order, and so on. Okay. So first of all, let's take a quick look at the description. In this case, we have a baseball that's thrown horizontally from the top of a building, and it lands on the ground 56 meters below. Okay, so we know the vertical displacement at landing. And we also know the final range. The ball lands 45 meters away from the base of the building. So, it might help if I draw a little sketch here of what's going on. So I'm going to say, all right, this is going to be the edge of the building here. The ball, I'm just going to draw the ball, not the person, right? This ball is thrown horizontally off the edge of the building. So that's V naught vector, okay? And then here's the ground far below. And this is landing right here. You know what? I'm going to leave myself a little more space. Should have started the sketch further to the left. Okay. So this is Y initial is at the top of the building. This is Y final here at the ground. Okay. This is X initial. We're here at the edge of the building. And this is X final at landing. Right. And what we know is that this range here, delta X final, is 45 meters, and this height of the building is 56 meters. So delta Y is negative 56 meters. If we stick with our axes the way we normally do, where the positive X direction is downrange to the right, and the positive Y direction is upward away from the center of the Earth. Now we have a couple of choices here. We can choose to put the origin either, it's traditional for the X direction to put the origin at launch, and to put the to put the origin at launch and not at landing. So let's say that at launch the baseball starts off at x naught equals 0, and then that would mean that at landing the position of the ball is positive 45 meters. Okay, I'm going to leave this space. However, in the y direction, well, we know the direction that the axis should point, which is upward away from the center of the Earth. But we have a couple of choices here. We can either choose y naught to be 0 at the top of the building, in which case y final would be negative 56 meters. Or we could choose y final to be 0 down on the ground, in which case y naught at launch would be positive 56 meters. I tend to prefer positive numbers over negative numbers. If there's enough known quantities, then I might as well make that choice. So let's call y final 0. Oh, let me also see what I stipulated for the graphs, okay? I said define y equals 0 at landing. So I might as well choose my axes for my problems to match what ultimately needs to happen over here for the graphs. All right, so here we're going to have this y position graph down here. So let's do that. All right, so let's call y final 0 meters down here at the ground, and the y initial will be positive 56 meters, okay, at launch. Well, I guess I didn't need to repeat that. Okay. All right, good. So now let's look at what the problem is asking us for. Okay, what is the ball's initial speed, v naught? So that is not given. We know the initial direction is exactly horizontal, but the initial speed is not given. That's makes the problem just a little bit more challenging, because it means we're going to carry around an unknown in all of these values here for v naught y and v naught x. It means the v naught itself is an unknown that we'll have to carry for at least a little while. Okay, and then later we're going to be asked about the final velocity. So right here at landing, we're asked what is the final velocity, right? Which is going to be some sort of vector that looks like this. And then in between, we have a path. So, and the path is, of course, as always, a segment of a parabola whenever something's in free fall. So down here at landing, we have v final x, and darn it, I didn't leave myself enough room here. I'll just draw right through it. So v final x, v final y, theta final, below the horizontal. All right, so that's what we'll need for part B later. All right, so initially for part A, all right, well, we're told the range, we're told the height of the building, and we need to find what is this speed right here, okay? Well, one of the first things I always do is I say, all right, take the launch velocity and decompose it into its components. So in this case, we can just do that by inspection. So v naught x is just equal to v naught times cosine of 0, which is just 1. V naught y, we can see by inspection, is equal to 0. All right, so good. So now we have those. Unfortunately, v naught is not a known quantity, but at least we have this ready to go. So now we know what to plug in for v naught x and v naught y in all these equations right here. Next, how am I going to get ultimately to a value for v naught, knowing the range and knowing the height? Well, if I look at my sets of equations over here, okay, here's this equation number 2 over here for horizontal components is where the range lives, okay? There's nothing that directly relates height, which is y displacement here and here, to range, which is x displacement there. But indirectly, we can relate height to range through time. Time is the one thing that appears in the equations in the horizontal box and in the vertical box. Otherwise, every other variable in those two boxes is separate. Time does not appear in this last equation, but it does appear in the second equation. So I think second equation here, and horizontal second equation and vertical second equation are going to be the keys to me being able to do this. All right, we can find the time of flight. We can't find the time of flight initially from the horizontal equation. Although we do know the range, this is the initial launch velocity, and that is not known. So we can't get the time of flight initially there, okay? But we can get the time of flight here from this equation. Height of the building, initial launch velocity 0, then I can solve for the time here. Great. So I think what I want to do is I want to use this vertical equation here to solve for the time of flight, then use time of flight separately afterward to plug into here to solve for that initial horizontal speed. Let's do that. So now I could solve everything algebraically first, but I think in this case I might just go ahead and solve for the time of flight just so I can see what the numerical value is. Okay, so we have y is equal to y naught plus v naught yt. Now I'm going to start by writing out the whole equation. Now, when you know things are 0 and so on, or you know the acceleration is negative g, you could go ahead and do that initial substitution right up front. I actually recommend always writing out the fundamental equation first and then showing the substitution. Now I can substitute a lot of these values, right? We're going to use t final, y final. At landing, the y position is 0. Okay. At launch, the y position is a positive 56 meters. Right. Then the next term is just 0, right? Because that initial y velocity right there is 0. And then this is negative g. You know what? Maybe I should have just, yeah, that's fine. This could also be the height of the building. We could have left that h for the height of the building. Let's go ahead and plug this in. I could have shown another step here where I set things to 0 that are 0, and then then plug in the values on one step after that. That's fine. T final is equal to 3.381 seconds. Now this is an intermediate value. Let's keep extra sig figs. It looks like a 2 sig fig problem, so let's keep a third or a fourth sig fig just temporarily. Next, finally, use horizontal equation number 2 to find V naught x. This last term, we don't even need to write this last term because we know that that acceleration is 0. Okay, so let's say that we launch from 0. Let's say that the final range is 45 meters. So that means that V naught x in that case is equal to 13.31. We know up here that the initial launch speed is just equal to the initial horizontal component because the two are exactly the same. So that tells us that the initial speed V naught is equal to V naught x, which is rounding to 2 sig figs, takes us all the way down to just 13. But if we're going to use that value in later calculations, let's keep extra digits on it. All right, let's find that final velocity now. So notice I already sort of sketched out the vector addition down here. None of these equations that we have here let us just jump directly to this final velocity magnitude or this final velocity direction, right? Instead, these equations only lead us to the final velocity's vertical component or horizontal component, right? And then we can use those components together to find what that total magnitude and total and direction are. So we got to first find the components. Let me switch colors. Okay. So oops. So first, let's do the horizontal component. That always tends to be the easiest because there's no gravity in that direction. So V final x, we know that all later times Vx is always equal to what it was at launch, right? There's no acceleration in the horizontal direction. So V final x is equal to V naught x, so that's just equal to 13.31 meters per second. Done. That was fast. And then V final y, for that, let's use equation number 1. V initial y, Vy, yeah, V initial y, plus ay t final. So it's equal to 0 plus negative 9.8 times 3.381. And that turns out, I asked my calculator what that is, and that's negative 33.13 meters per second. Ooh, coincidentally, very similar looking values, but I think that's just a coincidence. All right, so now we can find the magnitude and the direction. Okay, so now we're getting pretty familiar with how to do this, right? If you know the two components of a vector, how do we get the magnitude and the direction? The magnitude looks sort of like this Pythagorean formula. And I asked my calculator what that is, and it turns out to be about 35.71. And if I round all the way down to 2 sig figs, it comes out about 36. Okay. And then direction. inverse tangent of the y over the x component. Good news is all the meters per second are going to cancel out. So this turns out to be the inverse tangent of negative 2.4, negative 2.489. I asked my calculator what that is. My calculator tells me negative 68.1 degrees, right? Or I know that there's a second solution to inverse tangent 180 degrees away from that, but I can already tell almost at a glance, I mean, we know from this little diagram up here that we're looking for an angle that's negative, that's negative and between 0 and 90, right? So, and look, we can see it's that this vector v final is in the fourth quadrant. Another way to tell is from the components here. The components placed it in the fourth quadrant. So we just know that that's the answer right there, right? So the negative sign is replaced in English by the words below the horizontal in this case, because this is a trig direction. So clockwise from the positive x direction, right, will be in the negative, will be negative, right? So that's it. Okay, and then very quickly, let's do the sketches for this one as well. Let's qualitatively sketch the graphs, and I won't bother to label them with numerical values. You can do that as an exercise if you'd like. Horizontal components, horizontal component of acceleration, and again, this is time of landing, t final, always 0. What does the horizontal component of velocity do? At launch or throw, it has some v initial value, and it maintains that same exact value all the way until landing, right? There's no acceleration in the horizontal direction. And then finally, horizontal position. If we define horizontal position as being at the edge of the building, then we know that it starts at position 0 at time t equals 0, and then at landing, it winds up at some range, x final, which is 45 meters away. And it does so as a straight line. And how do we know it's a straight line? Well, we know partly by looking at equations of kinematics, but we also know that velocity is the slope of the position graph. So velocity is a constant positive value, position must have a constant positive slope for the position graph. Y direction. At all times in the y direction, acceleration has a value of negative g. Y velocity, we know that initial y velocity happens to start at 0 because the object was thrown horizontally, right? So that's the initial y velocity is equal to 0 right there. Here's landing. Now we know that the y velocity gets more and more negative all the way until landing. And then at landing, it has this very large negative value of negative 33, right? So there's a large negative value down here. This is v final y component. And how do I know that's a straight line? Well, again, we know from our equations of kinematics, number one, or number two, we know that acceleration must always be the slope of the velocity graph. So the constant negative value for acceleration means constant negative slope for the velocity graph. Finally, y position, we know we start at the edge of the building. So this is actually the height of the building right here, okay? At time t equals 0. And we know we end at the ground at landing. So we need to get from that point to that point. And what does the y position do as time goes on? Well, as time goes on, initially the y position decreases very slowly, and then it decreases a lot faster. So we're going to draw a sketch that looks like that. Initially decreases very slowly, and then later it has to decrease much faster. Okay. Something sort of like that. Now, I know because now at this point I've done a bunch of physics problems, I know that that is actually a parabola. So it would be wrong to draw like a quarter of a circle, for example, right? Also, I know that, and how do I know that? Because y is a function of t. Y is a function of time t. Looks like a quadratic with respect to t with a negative coefficient. That's 1/2 times negative g. Right? I also know that because here, velocity is always the slope of the position graph. So initially, the slope must be 0 because the velocity is 0. And then the velocity becomes a bigger and bigger negative number value at all times. So this has to become a bigger and bigger negative slope at all times. But the slope never becomes infinite, right? It's just a large negative slope. All right. All right, that concludes this lecture. So that's problems numbers 1 and 4. Questions 2 and 3 are very similar. Use the same set of equations as this one does. So use these same equations. Um, for free fall, so plug these values in for accelerations, and you can simplify the equations if you wish. And at any time you like, switch over to the problems that are online for credit and work on those for projectile motion.